Good day, viewers. I am creating these videos to help teachers of mathematics support their learners in making sense of mathematical concepts and their associated procedures and processes. And today I thought I'd look at solving quadratic equations through factorisation and through being able to factorise the quadratic expression. And you can see that I've already built on the left-hand side screen here with my algebra tiles. I built a factorized quadratic, and if you haven't seen factorizing quadratics, then there's a video for that on my channel as well. But the quadratic expression that I built is x squared minus 5x plus 6, and I factorize that into x minus 2, x minus 3, and now I want to solve that equal to 0. Okay, so I want to solve that equal to 0. Well, what I'm saying when I say I want to solve that equal to 0 is this area here represents that expression. So I want to find a value of x or values of x that will make this entire area 0. And what I want to draw pupils' attention to here is that in order to make this area 0, in order to make the area of a rectangle 0, then one of the dimensions has got to be 0. Either this has got to be 0, because that would shrink that all down to 0 length, and so I'd have 0 area, or this has got to be 0, so that would shrink all that down to 0 width, and so that would make the whole area 0. Okay, what I need here is some opposites, some inverses. And so we can look at, okay, well, what would make this 0? And what would make this 0, of course, if I replace the x here with a negative 2. And what's really nice, with a positive 2. And what's really nice here is that we can actually show that using the tiles. We can show, okay, well, what would happen if I replace that x with a positive 2? Well, then, of course, I'd need to replace this x with a positive 2 as well. And now if I built those same pictures, if I built that same sort of idea, but with this, then what we'd see is, well, this is a now 2 by 2 square. So there it is. It has that value of 4. And this is a negative 2 by 2 square in that case, but rectangle more generally. And so we get that negative 4 there. And this is a 3 by negative 2. So I'm going to get my negative 6 here. And then this is obviously negative 2 by negative 3. So I'm going to get my positive 6 here. And there's some things in here that I want to highlight to people. So I want to highlight to pupils how, this 6 rectangle in the bottom right is the same here, because those things were still negative 2 and negative 3. This wasn't dependent on the variable. It was dependent on just this negative 2 and negative 3, and that hasn't changed. That the length of this x and the length of this, which was my negative x, is the same length here, here, and here, and that my top left is the square. But of course, the other thing I want to highlight is the almost but not quite symmetry in these pictures. The fact that this square is the negative of this square, or this square is the negative of that square. Both, the negative relationship were both way around. And that this rectangle is the negative of that rectangle. And so what I've got here is I've got a load of 0 pairs I can create, and I could, if you like, actually go and physically create those 0 pairs and show that in the end all of that becomes 0. But actually it's not really normally necessary to do that, because I can just see that this and that top line there will have a value of 0. And the reason that has a value of 0 is because I've made this equal to that. So this size square is equal in size to this rectangle now, but they have opposite sign. And similarly, this rectangle is equal in size to that rectangle, because I've made this equal in size to that, but they're opposite signs. So this stays negative and this is positive. So this is the negative of that. And of course, I can show exactly the same thing. Didn't want another horizontal there. I can show exactly the same thing the other way, I can say, right, well, what happens if I make this x not positive 2, but if I make this x positive 3, so that this length becomes 0, and therefore the whole area should become 0. And I can do the same thing. I can say, right, well, come on then, let's make that 3, and therefore this x will become 3, but this will stay negative 2, because that was just negative 2. That wasn't dependent on the value of x. And similarly, this will stay negative 3. And what will happen now? Well, now, of course, what I'll have is I'll have 3 by 3 square up at the top. And then I will, underneath that, have a 3 by negative 3, what will be now a square. So that will be the negative 9 there for 3 times negative 3. And over here, I'll have negative 2 by 3. So that will be negative 6. And then, as always, I'll still have my 2 by 3 rectangle in the bottom, because that's still the negative 1 by negative 3. And that bit never changes. Doesn't matter what the value of x is. That bit never changes. And I can see again this sort of almost symmetry in this situation, can't I? But I can see now that this square is equal to this rectangle, which is actually a square. And I can see why that is, because I've made this x equal in length to that, but the opposite sign. So because this and this are equal, this becomes a square, and because this and this are equal in length to that, it becomes a square of the same size but the opposite sign. And similarly, this negative 2 by what is now positive 3 makes that equal in length to this, because this was always something that was 2 long by 3 wide, and it was positive because these two things were negative. So I can see again now that this time it's not horizontally that I get my 0 pairs, it's vertically that I get my 0 pairs. I get my 9 here, 0 pairing with my 9 there. I get my negative 6 here, 0 pairing with my 6 here. And that will still create that value of 0 altogether. You know, and what it's worth doing actually with something like this is looking at some other values for x and showing that you don't get the same thing here. So if I took a value of x to be 4, so I have x as 4. Then, of course, I'm just going to have a 4 square there. And then if I take my negative 3, which, of course, doesn't change just because the value of x changes, then I get my now negative 12, but I can see there's no real symmetry there. Although we still get the pattern of positive here and negative here, there's no symmetry there. These things are not sort of different. These things are not the same sort of size. They are different sizes. And similarly, you know, I could put my then negative 2 up here, which again doesn't change just because of the value of x. And that's going to produce the negative 8, but that doesn't help me in terms of creating a 0 here. And then I can take my negative 2 by negative 3, and I'll still have, as I always have, my rectangle of 6. And now, although I get, you know, some positives and some negatives, what I don't get is this almost symmetry where this bit is equal to either this or that, and this bit is equal to either this or that, but opposite sign, equal in size, but opposite sign. And that's because that only happens when the length of my x takes on the same length as either my, you know, my ones from here or my ones from here in this case, but the opposite sign. And that's how I make this 0, because it's reducing this value or this value to a value of 0. And of course, I could do that with several different quadratics. I could bring in some 2x squared there. But honestly, at this point, it's sort of relatively clear, and you might do it once or twice more with learners, but it's relatively clear that that's what's motivating this, that it's this make this 0 to make the area 0, because then we get these near symmetries going on. Whereas if I don't make either one of these lengths 0, I don't get that near symmetry. I just get 4 different sized rectangles or squares going on. And so, this is a sort of nice way of pupils connecting their earlier work on factorisation. And of course, this is always assuming that they've learnt about factorisation using this sort of structure. But it's connecting their earlier work to factorisation with then how we go on and develop and use it in terms of helping us solve equations involving quadratics. So that's my short video on solving quadratic equations using the factorised form. As always, I'd like to say a big thank you to MathSpot and its creator, Jonathan Hall, for this amazing website where I can use these virtual manipulatives to sort of help create all these videos. But if you haven't been onto his website yet, please do so. It's not just got the virtual manipulatives. There are all sorts of things on this website which are brilliant for maths teaching. If you haven't been on there, like I say, do make sure you go and check it out. It will make your life as a maths teacher easier having that site and knowing everything about it. And again, if you are interested in visuals and manipulatives and using those to sort of help make sense of mathematical concepts and their structures and their associated procedures and processes, then please do consider checking out my website. That is visiblemaths.co.uk. And among the many things you'll find on there, you will find a link to the publisher of my book. And my book is also called Visible Maths. That's why the website's called Visible Maths. And the publisher is Crown House Publishing. And on their website, which is linked through my website, you will find some sample pages or the chance to view some sample pages of that book. And if you feel like it would be useful for you, you can, of course, place an order. I will be creating these videos throughout lockdown and potentially beyond. So if you want to see a particular concept or process or procedure made sense of using manipulatives and visuals, then please do get in touch and hopefully I'll be able to create it for you. Thank you very much for your kind attention.